same cardinality. Now here's an example. Incidentally, this is completely trivial for finite cases. So the interesting examples come when we look at infinite sets. So I'm going to use the setup of the theorem, and I'm going to go through it in detail. Here, the x, I'm going to let x equals z and y equal 2z. And we're going to define the following maps. We're going to have a map from x into y. That's just the times 4 map. So anything in x, we multiply it by 4, it'll end up in y, because it'll in particular be an even integer. And we'll define the map G as the identity map. So G of y is y. So just to really nail this down, x has what elements in it? Well, it's the integers, so it has minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, etc. Right? And y is twice that, so y is just the even integers. And now our telescopes look like this. We start with, well, what I called x here, and that would be y. We have the map from y to x, which is g, and that's given, I called it the times 1 map. You can call it the times 1 map or just the identity map. And then here from z to 2z, we've got the times 4 map. That's there. And here we've got the times 1 map, and here we've got the times 4 map, and we just continue that forever. And that's the mapping telescope that ends in z. There's also a mapping telescope that ends in 2z, which I'm calling my y here, where you go from z to 2z by the times 4 map here, and you go from 2z to z by the times 1 map, and from z to 2z by the times 4 map. And now this is enough information to start looking at the ancestry of some of these elements. So here's a little box where I'm going to look at the ancestry of some of the elements of z. In other words, if we pick an element of z, we have to figure out whether it's in the image of g. In other words, whether it's in the whether it can have come from y. So 0 is obviously in the image of g, because g of 0 is 0. It's the identity map. And then if I back up and now I consider 0 in y, which is 0 in 2z here, we need something in z times 4 to equal 0. Well, 0 times 4 is equal to 0. And you can see pretty quickly that 0 has infinite ancestry. Now we go down and I'm going to look at 1 in z. Well, is there anything from 2z that maps to 1? In other words, is 1 in the image of the injection map from 2z to z, or in the image of the identity map from 2z to z? Well, no. Only even integers in 2z, so only even integers can come out. Now 2 is in the image, so it's got ancestry, so 2 maps to 2 under G. And then we look at 2 and we see if it's in the image of the times 4 map. Well, no, it isn't. So here's infinite ancestry, here's something with odd ancestry, here's something with even ancestry, because there are 2 elements in the ancestry. Odd ancestry again. 4 has odd ancestry. Notice that 4 goes to 4 under G, and 1 goes to 4 under the times 4 map, which is F. So that's F there, and that's G. This is 6. Let's see, 5 is odd ancestry, 6 is even, 7 is odd. 8 is another interesting one where 8 goes to 8, 2 goes to 8, 2 goes to 2, but there's nothing here that maps to 2, and you can check that. So this is even ancestry, but length 4, and you would continue to do that. Similarly, we can look at the ancestry of elements in Y, and again, we're thinking about the same thing. We're looking at the elements in Y. What are the elements in Y? They're only even integers. And we look at those that are in the image of the times 4 map from Z. So 4 is, 8 is, in the image of the times 4 map, and 2 is in the image of G, so we have an ancestry of 3 here. So infinite ancestry, odd ancestry, even ancestry, odd ancestry, odd ancestry, odd, even, odd, and then even, odd, even. And I think with a little bit of work, not a whole lot of work, you guys can come to the conclusion that x infinity is equal to y infinity is equal to just the set 0. And x odd, which may take you a little bit of work, but think this through, I think you'll find out that it's odd numbers. I'll say numbers of the form 2l plus 1 times some power of 4, or I'm going to write it as 2 to the 2k, which you might have, when you first looked at this, come up with 2l plus 1, so odd integers, including 1, times 4 to the k. Those are the same thing. X even turns out to be odd numbers times odd powers of 2. I'm running out of letters here, but hopefully you get the idea. And I claim that's all the integers. All the integers can be represented as one of the following. Either 0, 2l plus 1 times 2 to the 2k, or 2m plus 1 times 2 to the 2l plus 1. So you can play around with that if you don't believe me. And you could similarly look at y infinity. Well, we already did that. Y odd. Let's see. What is y odd? Is actually, not surprisingly, is even numbers, but not quite all even numbers, right? So which even numbers do we have? We have 2, 6, 10, 14. So those are odd powers of 2. So an odd number, 2l plus 1 times 2 to the 2m plus 1. I should have used the same letter here, but you'll notice the the correspondence there. And then y even is, let's see which ones have even, are those that are odd numbers times a power of 4. There. Oops. Odd numbers times a power of 4, so 2, I don't know, it doesn't really, I'm getting caught up with these letters, 2k plus 1 times 2 to the 2m, whatever. And now, how does h of x work? Well, h of x are bijection, and you can clearly see in this example, which you may think is a misleading example, but you can clearly see the relationship between x even and y odd, right? And x odd and y even. Now our map is going to be, and this is supposed to be an H that maps Z into 2z, and this is supposed to be one-to-one and onto map, and it's going to be, oops, sorry, miswrote that. It's going to be f of x if x equals 0. It's going to be f of x if x is in x odd, and it's going to be g inverse of x, which g and g inverse are both the identity function, so it's not all that interesting, if x is in x even. And you can check that this is 1-to-1 and onto. Ta-da! And just because I was asked, I will draw one more bee. A smiling bee. I don't know. There's not enough legs there.